I'll be giving a quick overview of our jitter characterization campaign for the HyTI SAT. So an outline of my presentation, I'm quickly going to go over the HyTI mission at a very high level, then I'm going to talk about what jitter is and how we usually measure it, and then really get into the meat of the presentation, which is introducing our optical metrology system, then go into how we collected data, analyzed it, and how we set up our experiment to measure jitter. Finally, moving into some results, and then wrapping up with some advantages and limitations of the system, as well as some conclusions. So an overview of the HyperSpectral Thermal Imager mission. This is a NASA demonstration mission to obtain high spectral and spatial long-wave infrared images from a 6U CubeSat. It will operate in low Earth orbit and observe volcanic sulfur dioxide emissions and precision agriculture metrics. Because it is imaging in the long-wave infrared, it features a crowd cooler, and this crowd cooler, combined with the CubeSpace reaction wheels, introduce jitter. And so, what is jitter for those of you who aren't familiar? Jitter are micro vibrations of the satellite platform that cause periodic instability in the satellite's attitude, and this is caused by moving or vibrating parts. And in this image, there's the laser right there, you can see the effects of jitter on imaging. This left here is an image that is uncorrected for jitter, it's blurred. And as you move right, the jitter correction kind of kicks in, and it's nice and sharp. This image here is a centroid map on the focal plane, and you can see this kind of random semi-periodic structure there in the jitter against the circled requirement there. And jitter is a fundamental limitation for all satellites as it affects their pointing precision and accuracy. But smaller satellites are actually disproportionately more affected, and this is because these vibrating parts, like the crowd coolers and the attitude control systems, make up a larger percentage of their mass when compared to larger satellites. And that's shown here in this figure, where we have launch mass down here and RMS pointing stability here. And here you have missions like Kepler, James Webb, and Hubble. Very high launch mass, very exquisite pointing stability. And as you move down in launch mass, you can see a more modest ability to point. And HyTI sits, given its requirements, about right here. And so for HyTI, jitter in the integration rate and the frame rate reduces the quality of the data, and specifically by changing its effective spectral and spatial sampling rates. And so we currently measure jitter on the ground, usually using piezoelectric dynatometers and finite element analysis. But for piezoelectrics, these require expensive specialized setups, such as this one, where you're placing your test subject on a adapter plate and a dynatometer. And these plates often limit the size of the subject that you can measure, as well as the frequency that you can measure up to. Once you get the disturbance data from these piezoelectric sensors, you move on to finite element analysis, where you obtain a system transfer function, and then which is usually based on a finite element model. And the issue with this is that that's computationally expensive, and the accuracy of your finite element analysis depends on the accuracy of your finite element model, which is generally known to decrease as your frequency of interest increases. And so all in all, system parts and components can be manipulated or altered on the ground to achieve more optimal jitter characteristics as you test, but fundamentally, your analysis fundamentally relies on the accuracy of the model. In orbit, you can do a couple of things. You can use high-performance attitude sensors that really just measure jitter pixel as a function of time, like this. Or you can do something more creative, like using an auxiliary image sensor or an optical correlator to measure the movement of subjects between consecutive frames. And while this accurately measures jitter in situ because of your free boundary conditions, and you don't need a finite element model, at this point you can do no more than to characterize jitter in your system because you've already launched your satellite. And so for us, we asked, can we develop a metrology system to measure jitter on the ground with commercial off-the-shelf components that achieves high accuracy without a finite element model? And so the principle for our metrology setup is to use the stationary laser and measure tiny deflections caused by the satellite. And so in this block diagram here, the laser feeds a collimator. The collimator produces an incident beam onto a mirror that is mounted to HyTI. Jitter in HyTI induces vibrations or deflections in this mirror that are measured by a lateral effect position sensor, which reports voltages to an auto aligner. And this analog position information is put through an analog to digital converter, and out you get digital position or digital displacement information. On the right, I have a graphic of this metrology system integrated into the HSFL's ADCS testbed facility. HyTI is sitting on its 6U side on the support jig there. The mirror is placed there. The laser collimator, I just traced the path of the incident beam, and I've indicated the directions at which the lateral effect position sensor records data. So the X direction data runs parallel to the ground, and the Y direction data runs perpendicular to the ground. I've indicated the throw distance L because what we're going to do is we're going to divide these displacements by L to obtain an angular displacement. So really what we're interested in is physically, correlating our X and Y direction data with jitter as HyTI will be deployed. So the X direction data will correspond to in-track jitter, and the Y direction data will correspond to our across-track jitter. Great, so we write a getData.py function to collect some time series, one in each direction, like shown here. This is just angular displacement as a function of time. And then we take the Fourier transform and convert them into power spectral density plots to investigate the frequency content. And these are just the PSC plots of the time series that you saw before. And so to calculate the jitter, we use the fact that the variance of a zero mean random signal is given by the integral of its PSD between a minimum and a maximum frequency. It's just given there. And so basically what we're doing is we're picking a frequency down here and just integrating all the way out to 500 hertz, which is the limit of our ABC. And I'll come back to that later. And so what we want is the integration rate jitter. But the only thing, given that integral we can solve for, is the frame rate jitter, because 139 hertz is less than 500 hertz. But we assert that the frame rate jitter should bound the integration time jitter, and we'll use the frame rate jitter as a metric for analysis. And so once we've integrated both power spectral density plots to obtain the variances in both directions, the total variance is just given by the sum of the two, and the n sigma value is just given by n times the square root of the variance. And for HyTI, this 1 sigma, or the RMS pointing error, is requirement is 2.89 arc seconds. So procedurally, we're also interested in attributing modal frequencies to vibrating sources. And so what we did was we created permutations by incrementally adding or altering vibrating sources, and then looked at the results in the frequency domain, and then associated the difference to sources. So in this table right here, it kind of runs through all the configurations that we tested, and so the idea is that as you work down the table, you are only changing or altering one vibratory source at a time. And so in configuration 1, we have all of our active sources off, and in configuration 2, we just turn on the cryocooler and the payload. In configuration 3, we turn the air bearing on while leaving all of our active sources off, and so on and so forth. I'm going to kind of really go into depth about what the configurations are later, but the idea of this is basically we're doing something similar to a parameter sensitivity analysis with the vibratory sources. And so once you have the PSD for each configuration, we used an algorithm to find the peaks in the PSD plots, and that's just given by these black marks there. And then each peak was fit to a Lorentzian profile, and the fit parameters were recorded. The results for each configuration are tabulated like so, where we have the in-track frequencies identified, which is just the center of the fit, the amplitude, which gives us an indication of the power of that frequency in the signal, and the full width half max, which gives us an indication of error or uncertainty. This is repeated for both the in-track and the across-track. And then really what we're interested in is to associate the sources with frequencies, we compare the tables for differences between configurations. And so as an example here, say you have configuration n and n-1, right? New frequencies in configuration n are highlighted in green, and similar frequencies are in orange. And so between these two configurations, for example, the only difference was the cryocooler on. And so you can see that, for example, in the in-track direction, this configuration 2 had a peak at 60 hertz, which is not present in configuration 1 with the cryocooler was not active. And so because the only difference between those two configurations was the vibrating cryocooler, must have had to be the cryocooler. The idea behind the similar frequencies is that, for example, in configuration 1, it's very hard to see, but that's 120 hertz there, and there's also a 120 hertz frequency there. And you can look at the amplitude to compare between these two values. And so the amplitude difference between these two trials is about 3 orders of magnitude. And so from that, you can safely say that the cryocooler contributed to a mode at 120 hertz in configuration 2. And so in summary, we use this optical jitter testing to quantify the jitter by integrating the PSD plot state variances, and then to understand system dynamics, we did this adding and altering of vibrational sources incrementally and to note any changes in the power spectral density plots. And so here I'm going to go over results each by configuration. So in configuration 1, we have all of our vibratory sources off, and this is just to assess the ambient environment in the clean room. And so we see a host of frequencies that occur in the cross-track direction and a couple in the in-track, and that's just likely seismics from the clean room. And so we don't calculate a jitter value because the air bearing is off, and it would be a really meaningless value. But this is important because in the next configuration, we turn on the cryocooler and actually see brand new frequencies. So remember, green frequencies are new frequencies are highlighted in green that were not present in the previous configuration. And similar ones are in orange, and then we note the source of that frequency there. Again, no jitter value is calculated because the air bearing is off and your motion is constrained. But the idea of this is that you can really see the cryocooler operating at 60 hertz, and it generates a lot of the higher order harmonics in the across track, and especially in the in-track direction. So in configuration 3, we turn on the air bearing, and immediately we see the absence of all those frequencies that we saw before, which makes sense because we've now isolated the jig or the satellite from any kind of seismic vibratory activity, and so we begin the calculation of these jitter values, even though they're kind of at this point really not that useful, but comparing them in between configurations is helpful. This peak at 120 hertz, it is similar, like it's highlighted in orange because it is similar to a frequency that was present before, but the source is different, and this is noise. And this is generated from the imbalance in the air bearing causing that laser beam to walk off the sensor. And if anyone's interested, I'd be happy to talk about that in the questions. And then in configuration 4, the only difference here is we turn the ADCS electronics on. And so the reason for doing this is that we have a separate configuration that does not add a vibratory source. And this is a good way of sanity checking the work for any systematic errors or issues with the metrology system. So again, same thing, 120 hertz with the noise. And here's where things kind of get interesting. Now we turn on the X direction reaction wheels at 3,000 RPM. We see a significant drop in the RMS pointing value below 1 arc second, but we still see that same noise mode. And interestingly, we don't see a peak at where we might expect one to see, which is about 50 hertz. And this actually makes sense given the dynamics of the system. And again, in the interest of time, I would love to go over it if anyone has questions about that. Right, so next configuration that we tested was we turned the X direction reaction wheel off, turned the Z direction reaction wheel on at 3,000, and now we actually see some new frequencies. So 0.03, this is air bearing drift, but in the across track direction, you see a subharmonic at 11 hertz and a peak at 58.27 hertz. And whether or not this is from the Z direction reaction wheel, we actually aren't sure. The only way to really confirm that is to look at the encoder data for the wheel, which we unfortunately didn't have for this trial. But you can actually see a very large drop in the jitter values. And so finally, and I think the most interesting configuration that we actually were able to test, we run both the direction reaction wheels, and now you can actually see that the jitter values remain about the same, but we actually introduced some new frequencies here. At 210 and about 368 hertz. This 210 hertz occurs in both the in-track and the across-track direction, and this 368 hertz occurs in the in-track direction. And so this was really interesting because it really demonstrated the, I guess, non-superposition, right, of these jitter sources and how you can, testing an integrated system like this is really, really beneficial. And so wrapping up, some advantages and limitations of the system. Advantages that we were able to attain PSDs for jitter analysis without the use of a finite element model. All the components for this system are commercially available, and you can purchase them right now if you wanted to. And there's no dependence on natural frequencies for the system. A couple of limitations though, we don't have data for arguably the most compelling case, which is the cryocooler and the reaction wheels. running. And in my opinion, this is both a benefit and a curse of testing on a system that is ready to be delivered. Everybody else is trying to run their testing, and so it's like, oh, we'll get to yours if we have time. But that's okay. I think we got some interesting results here. Imbalance in the air bearing led to some noise in those measurements, as you saw those kind of ghost spikes at 120 hertz. The support jig that you use alters the moment of inertia. It adds about 30% of HyTI's mass, kind of in that bottom direction. And so we have to really work on trying to understand the response scaling for that. And in my opinion, the biggest limitation is the ADC samples that, we have a really slow ADC that only samples at 1 kilohertz, but this is readily solved by just purchasing a faster ADC. And so in conclusion, I present an optical metrology setup and methodology to conduct jitter analysis in the frequency domain, and you can really use this to investigate disturbances in components, subsystems, and fully integrated systems. We performed optical jitter testing on HyTI and found that the reactional jitter remains under the 2.89 arc second requirement. We identified frequencies associated with some of those vibrating sources, and for future works, we really want to compare these measurements with in-situ measurements of jitter obtained from HyTI, and with HyTI already delivered, we plan to use this metrology system extensively in the development of HyTI 2. I would like to acknowledge the support from these organizations and individuals, and will be happy to take any questions.